Hello, good morning students. Today we are going to discuss about the Paschen-Back effect. So we know that the anomalous Zeeman effect. What is the anomalous Zeeman effect? When an atom is placed in a weak magnetic field, the splitting of a spectral lines will be more than 4 components or 6 components, etc. When the atom is placed in a strong magnetic field, each spectral line will be split up into 3 components. Okay. In anomalous Zeeman effect, in the presence of weak magnetic field, the J bar vector will precess around the external magnetic field. This precision is called Larmor's precision. In case of a strong magnetic field, the L bar orbital angular momentum vector will precess around the external magnetic field. So if you increase the strength of the magnetic field from weak magnetic field to strong magnetic field, this anomalous Zeeman pattern will be converted into normal Zeeman pattern. This effect is called Paschen-Back effect. So what is Paschen-Back effect? When an atom is placed in a weak magnetic field, each spectral line will be split up into more than 3 components. So if you increase the strength of the magnetic field from weak to strong, this splitting of spectral lines will be converted into more than 3 components into 3 components. So this transition from anomalous Zeeman pattern to normal Zeeman pattern is called Paschen-Back effect. So once again I will repeat, the transition from anomalous Zeeman pattern to normal Zeeman pattern by increasing the magnetic field from weak magnetic field to strong magnetic field is called Paschen-Back effect. In a weak magnetic field, the J bar vector only precesses around the external magnetic field. In a strong magnetic field, L bar vector only precesses around the external magnetic field. If you increase in a weak magnetic field, this J bar vector will precess around the external magnetic field. So what is J bar? J bar is the resultant sum of orbital angular momentum and spin angular momentum. So if you increase the strength of the magnetic field, the coupling between L bar and S bar will break up. This individual L bar and S bar will precess around the external magnetic field. So during this transition, instead of revolution of J bar vector, this J bar vector will be split up into 2 components, one orbital component and second one spin component. During this transition, L bar and S bar will precess around the external magnetic field. This precision is also called as Larmor's precision. So hence the interaction energy delta E is the resultant sum of interaction energy due to the orbital angular momentum plus interaction energy due to the spin angular momentum. So during this transition, the coupling between L bar and S bar will break up. So this L bar and S bar individually will revolve around the external magnetic field. Hence the interaction energy is interaction energy due to orbital motion and interaction energy due to spin motion. So we already discussed, so the interaction energy due to orbital motion as it is the dot product of angular velocity of the angular momentum and the z component of orbital angular momentum. So the interaction between L and external magnetic field is the angular velocity of this revolving orbital angular momentum with that of the component of L bar along the external magnetic field. Since the direction of applied magnetic field is along z direction, here we will take the component of L along z direction. So this omega is, what is omega? Omega is mu L by L into Bz. So what is Lz? Lz component is the component either in the direction of external magnetic field or opposite to the direction of external magnetic field or in the same direction. That means it will be represented with the quantum number ml. This quantum number should be quantized, that is h by 2 pi. Here omega is mu l by l into bz and lz is ml into h by 2 pi. So mu l by l is e by 2m into bz ml h by 2 pi. So this is the interaction energy between the L bar and external magnetic field. Similarly, the interaction energy between the S bar and magnetic field can be represented as delta E of S is equal to, in the same way, it is also the dot product of angular velocity of S vector multiplied by the z component of S vector. So omega S is nothing but, here omega is mu L by L, here omega is mu S by S into Bz, Sz component is L is Lz h by 2 pi, Sz is Ms h by 2 pi. So mu S by S is, we have already derived the expression for mu S by S is 2e by 2m, where 2 is the Landau splitting factor. So hence mu es by mu e is equal to 2e by 2m into bz ms h by 2 pi. So this is interaction energy between L and external magnetic field. This is the interaction energy between S and external magnetic field. Hence, the resultant interaction energy is the sum of the resultant interaction energy of orbital angular momentum vector and the resultant interaction energy due to spin angular momentum vector. So, what is delta E of L? E h by 4 pi m multiplied by bz into ml plus here 2eh by 4 pi m bz into ms. Here the common terms are ebzh by 4 pi m, ebz by 4 pi m multiplied by h. So the remaining term in the first equation, the remaining term is ml. So here 2 ms. So this is the interaction energy in a Paschen-Back effect. So then the term value is, what is the term value? Delta T is equal to delta E by hc. So we have already calculated delta E. What is delta E? Ebz h by 4 pi m divided by hc of ml plus 2 ms. H get cancelled. The remaining terms are ebz by 4 pi mc of ml plus 2 ms. This constant here, E is the charge of an electron, external magnetic field is constant, m is mass of an electron is constant, c is velocity of light. All these are constants which is represented with the letter called L dash. L dash is nothing but Lorentz unit multiplied by ml plus 2 ms. That is, the separation between the two lines depends upon ml plus 2 ms value. So this is regarding the Paschen-Back effect. Next, consider an example to draw this Paschen-Back effect pattern. So what is delta T? Delta T is L dash into ml plus 2 ms. So consider 2p to 2s transition. So for 2p the L value is 1, S value is 1 by 2. So for 2s state L value is 0, S value is equal to 1 by 2. So here we need to calculate ml plus 2ms values. Before that we will calculate ms, then ml and ml plus 2m.